Welcome back. We are going to work out this exercise, bringing an illustration to that method, the method previously discussed, this theorem, which looks a little bit like a mouthful here and a little bit like a handful, but we want to know that what this theorem is telling us is how to construct the vectors in the vector form of the solution set. And those there are two types of vectors. There's a vector of the so-called fixed vector, and that vector will contain zeros on entries corresponding to indices of free variables, and then it will contain the values on the last column of the RREF. And then there will be vectors in a linear combination that are exactly n minus r of those vectors, and the entries of those vectors are going to have a 1 for locations corresponding to free variables, and they're going to have zeros and also locations corresponding to free variables, and then they're going to have the negative of the entry and the RREF. Okay, so we're going to work out this example to illustrate this. So in this example, we can see here that first little r is equal to 3. Second, the number of columns in this matrix is n plus 1, and there are exactly 6 columns there, right? So we say that n plus 1 is 6, and this implies that n equals 5. So the number of variables is 5. So what we want to do next is to think, okay, look, we have a solution that looks like x1, x2, x3, x4, and x5. Okay, we're gonna rewrite. We're gonna write this solution in something that has this format. Here's the fixed vector, and then there will be another vector. So another piece of information that we derive from here is that the set D, in this case, the set D, okay, the set D contains indices 1, 3, and 5. On the other hand, the set of the indices with the free variables, set F, contains indices 2, 4, and 6, the last column, right? So in this case, we know that the free variables are going to be x2, they're going to be x2 and x4. That's what this set of indices is telling us. So that means that in the solution vector, x2 and x4, excuse me, x2 and x4 are going to be used as the coefficients in the linear combination. So we're going to write here x2 and we're going to write here x4. And the things to watch out for are the entries of the dependent variables. So the fixed vector is part of what the theorem is telling us is that the fixed vector is going to contain numbers from the last column in the RREF, but also we're going to go to according to the indices of the free variables, right? So according to the indices of free variables, so here is x2, here is x4, okay? And so according to those indices, we're going to put zeros on the fixed vector. So we're going to put zeros on location 2 and also on location 4 of this fixed vector. Remember, these are blank vectors. Each of them is going to store 5 entries. And also on the vectors that are part of this linear combination, we're going to multiply, we're going to locate, we're going to put a 1 on position 2 of this vector. And in position 4, we're going to put a 0. That means that when this x2 multiplies, when we carry out this scalar multiplication, we're going to end up with an x2 expression on the second entry and with a 0 expression on the fourth location. And when that is added to this other vector, so this misses plus sign, then that is not going to interfere. So that means that for this vector on location 4, we're going to write a 1, but in location 2, we're going to write a 0. And it's a similar idea. When the scalar multiplication is carried out, there will be an x4 on location 4, and there will be a 0 on location 2. And when these two are added up, then there will not be any interference. The other thing that we have to do now is to collect the terms out of the augmented matrix, the row reduced augmented matrix, that are going to be positioned now. There are 3 positions that are blank, and now we're going to collect those terms. So we have numbers. We have the numbers 9, minus 8, and 3, and that's precisely what we're going to write here. We write 9, minus 8, and 3. Okay, so this is what the fixed vector looks like. And what we do next is to fill out those 3 positions on each of the vectors in the linear combination. And that is the information that comes also from the RREF, but this information will come in terms of taking the negative of the entries in the RREF. For example, that 3 is going to be written here as minus 3, and this 6 is going to be written as negative 6. Then looking at the second row, we see that there is a negative 2, which will become a positive 2, and there is a 0. And looking at the last row of the RREF, we see that we find zeros in those positions, and those are precisely the numbers that we write here, 0 and 0. So what we would say is that this solution set is given by this fixed vector plus this linear combination, where you can verify this by writing the solution set in the all form. Okay, and you should find that this matches your calculations. So in summary, we can write the solution set as a fixed vector plus a linear combination with 2 vectors, with 2 scalar multiplications in that linear combination. X2 and X4 are the scalars in that linear combination, so we write this fixed vector plus that vector, each of them multiplied by X2 and X4 respectively. Then we write a vertical line, and then we write X2 comma X4 belong to C, are members of C, and then we close. This is the set notation, and this is exactly what we wanted to express, how to compute the solution set of this of the linear system that corresponds to this RREF, this augmented matrix in reduced form. This is precisely that solution set now expressed in vector form.